nobody wants that. So before I get started, so basically, I'm just going to give an overview of fuzzing. If you know what fuzzing is, feel free to tune out for 2 minutes. But in case you don't, I figured I should talk through it. Basically, the original form of fuzzing was catting dev random into your application and just see what happens. You take a base 64 decoder that's not properly hardened and pipe random data into it, and you might crash due to buffer overruns or whatever the case may be. And obviously, since then we've advanced quite far. Now we use tools like AFL++, or like the fuzzer I'm talking about today uses libAFL, which use guided mutations based on coverage of the program under different inputs, based on comparison values that are logged during execution, based on values that are profiled during execution, and so forth, all the way up to techniques of like taint analysis, where we observe the data flow from our input through the program to figure out how our input is affecting specific parts of the program to mutate it better, and symbolic execution, where we use formal methods, abstract interpretation type approaches to figure out how to build inputs that satisfy particular paths through a program. So fuzzing's come a long way, obviously, and it's super effective. So if you've ever seen the classic OSS fuzz claim, they used to say 10,000 bugs. Actually, it's closer to 40,000 now, found just by fuzzing various open source projects pretty much continuously on Google Cloud. And if you were paying attention to the news yesterday, there was a bug that was found in most UEFI distributions called logo fail, where there was a bug in the parsers for the little splash screen logo image that pops up when you boot your computer. That was found also with fuzzing of UEFI platforms. So I feel like this is a bit of a timely talk here. So basically what we did is we looked at the fuzzing landscape of UEFI and we said, okay, so there's a few tools. One is one that we at Intel maintain called KFL. It's great. It's really good at fuzzing, specifically the Linux kernel is what we mostly use it for, but we also have used it to fuzz OBMF pretty extensively. And we also have a tool called HBFA, which is EDK2 contribution, which essentially rehosts EDK2 firmwares to run in user space so that we can use typical fuzzing techniques for user space applications with them. But the missing piece was basically both of those methods require either a lot of setup and specific conditions, or in the HBFA case, it requires you to write a bunch of code to handle all of the like hardware specific stuff. So you're running your firmware in user space. Obviously, if you have a handler that does something with power or with attestation using specific like SBX calls or TD calls or something like that, you have to write a bunch of code to basically hook those and simulate them when you run it. You can't actually run against the real hardware because you're running in ring 3. So there was kind of a gap where we said a lot of people probably could do with a tool that'll make it a lot easier for them to fuzz their firmware. So at Intel, we mostly use a simulator, which actually has already been mentioned a few times today, called Simix. It's a full system cycle accurate simulator. We have packages for basically every platform available on our website, with several open packages, including platforms up to Sapphire Rapids and Alder Lake. So basically our current CPUs are available for, it's not like the most simulators where you get something that's 10 years old, like you can only use Nehalem. We publish packages for pretty current processors, so it's reasonably useful externally to Intel as well. And what Simix gives us is the ability to simulate all the way from device firmware and initial firmware images, all the way up through the whole stack of our software, including Dixie drivers, UEFI applications, the OS, whether it's the Windows or Linux. We can simulate through the kernel, we can simulate user space, everything. We can run full system on it. And so we looked at that capability and we said, all right, well, let's just add a fuzzer to it. So that's what I've done. Basically, we released a couple weeks ago. It's on GitHub, Intel/TSFFS. I'll put in chat. And the fuzzer is a Symix package that you install into your Symix installation, and you get a interface through scripting to fuzz whatever you're running in Symix. So it tries to stay out of your way as far as what you can do with it, and so it's built. Sure, that's not my group, so you'd have to ask somebody else about that. I hope so. But so we have Symix, which simulates stuff, and we have TSFFS, which is a package for Symix, which lets us do fuzzing. And we combine those to basically enable fuzzing. We've tested UEFI applications up through user space. Right now I'm working on setup for Dixie drivers. And we've also tested our IFWE fuzzing internally. And we'll eventually test some of that with open packages from EDK2 platform. I haven't done anything with core boot yet. I know I've heard that mentioned a few times, and I haven't looked at it because I haven't had time, but it's also kind of on our roadmap to test and make sure that the fuzzer works for core boot. So before I jump into demonstration, any questions kind of about fuzzing, about what we've built, kind of general stuff?
I guess like my question is about these models, because when I was working with Symix, when Symix was, by the way, it was initially developed, I guess, by Russian team, if I recall correctly, and this was transitioned. By the way, I was BIOS developer in Intel back in my days, like 8 years ago or something. The most valuable thing was these models, the definition of models, especially for new processors. And yeah, I guess like, so let's say I would like to develop Dasharo on Symix. Like how far, what's the most recent version of processor model I can get?
Most recent is Sapphire Rapids.
Okay, so this is like a server. It's a server. There are no client models?
There's also client. So most recent client is
Meteor?
either 12th or 13th gen. I don't remember.
14th. Meteor Lake, yeah?
Meteor is 15th.
Yeah, I don't think Meteor Lake is public yet.
Okay.
Yeah, and through NDA probably Meteor Lake and Arrow Lake could be available, I guess. But yeah, for public, we should wait a little bit longer after launch date, at least.
Yeah, so Rowan, to not hold you with this, but the Symix part is very interesting. And if you can, I know that part of the Symix team is in Poland, and like some of them wanted to connect with me. I don't know these people. I probably know some names. If I will but I don't know who joined that team. I know a bunch of names from Intel Poland, but but if there is any synergy, if you work with those people, if we can somehow connect each other. By the way, 3MDEV got all the NDAs with Intel, so I guess like this is like just to like not block you with some communication. Although I guess there are some limits to that. So it would be great if you can connect with people that are responsible for these models. And I know there is interest in these models, and maybe and what you say, core boot, like using core boot in this environment. So I would like to push in maybe in 2024 a roadmap for Dasharo on Symix. And one more thing, there is open security training to Zeno and I did the evaluation of the CMix for the OST2, and there are some materials there regarding CMix usage for learning the open source firmware, learning offensive and defensive security using CMix. Yeah. So for those looking for more knowledge and want to learn.
Yeah, definitely. I think that's all great ideas. I mean, obviously, if you have NDA stuff in place, we can talk offline about getting things set up with 3MDev. But I'm sure the Cimex team would be happy to help with that. They're always looking for new stuff to try out and new firmware to run on the system and all kinds of things. So I'm sure people would be excited about it. Any other general questions before I kind of demo how everything works?
Another Cimex question would be if it supports TXT.
I don't know, but I think so.
Okay.
So just like that's, I heard rumors about some leak where there is emulation of ME. I know that you cannot comment on that, but I'm just saying there is some stuff that even can emulate ME. So one can even introspect and understand that part for those who are not afraid leaks. 3MDev is afraid of leaks. We're not touching that. Yeah.
Yeah, I haven't heard about that. Kind of out of my lane. I'm more focused on just enabling fuzzing on stuff, but feel free to download the public version and try and use it on stuff. I won't stop anybody from looking around. But yeah, like I mentioned, we have recent server models, so I would expect that most things you can do on a real CPU, you should be able to do on the modeled CPU. All right. Let's jump in here. So I'm doing something brave that I don't usually do, and I'm doing a live demo. So we'll
yay!
see how it goes.
Let the spirits of live demo be with you.
Yeah. All right. So I've got EDK2 downloaded here, and we're going to be looking at a UEFI application just because it's a little simpler. I didn't want to, scroll through 500 lines of Dixie driver with everybody. We've got a main down here. Is this big enough? Let me know if it's not. So we've got a buffer, and we are calling X509 verify cert on half the buffer as the certificate and half the buffer as the CA certificate. And obviously, this is pretty contrived. And right now, this will not do anything because this is uninitialized memory from allocate pages. But what we can do is, if you can imagine and extrapolate this to basically any scenario, is the way the fuzzer works is you send input to something. And that's kind of the way that libfuzzer and user space fuzzers are designed to work as well, as they have, they give you some test case data, and it's your responsibility as the harness author to write a harness. So that's what we're going to do today, is we're going to write a harness for X509 verify cert. So let's imagine this is the API from EDK2 or whatever firmware you might be looking at that you want to fuzz. Basically, what we do is first we include this file, which just does the CPU ID, which is basically the way Cimex does, like a VM call. You can think of it as you can pass some information from your simulated system to your host system via what's called magic instructions. So we just use that functionality and we wrap it in a couple of convenience macros, but this is just doing a CPU ID. So we do our CPU ID, which passes the buffer we want to put our test case data into, and pointer to the size of the test case data. So basically this says, all right, fuzzer, don't give me more than a page of data, because we don't want the fuzzer to be overrunning our test case buffer. And then we print it out and hex dump it. This is just for demonstration purposes. And then we call our API on it. after that, we don't expect this to pass because we're basically passing random data into certificate verification. So just for demonstration purposes, we're gonna do a harness assert if the status is true, which means that this is successful. And otherwise, we're just going to stop. So basically what happens is at the point where we call this harness start macro, the fuzzer will take a snapshot of the full system. And then each iteration of the fuzzer, it'll write a new test case to our buffer and write the size of that test case to input size. It'll run. And then when it hits either a timeout, our assertion, or our stop macro, it'll stop the execution, it'll reset to the beginning, and it'll run again with a new test case. So basically what we'll see is it'll just run, essentially we're just creating a loop in our code, but with a new input from the fuzzer. And it's a pretty simple API, but it ends up being really flexible. You can write your fuzzer input to disk and then run something that takes the input from disk and does some verification on it, all kinds of stuff. So basically, sky's the limit, and as much effort as you are okay spending writing harnesses, the better results you can get out of your harnessing. For example, harnessing PNG parsers from common BIOS if you were doing this 3 days ago and not today. So we'll go ahead and compile this. So this will create just a binary with our little harness hooks in it. And after that, we'll go ahead and start using Symix. So we have a project set up. And the way Symix works is you can either write a script in Symix scripting language, which is a pretty simple kind of bash-like language, or you can write your script in Python. And so I've written mine in Symix script because it's much simpler. So basically what we're going to do with this script, you'll see I have the fuzzer stuff commented out at the top, and we'll get to that later. But what we're going to do is we're going to load a UEFI shell on the x86 platform. This will just use the default x86 CPU, which is a pretty old one, but you can, I have examples in the repository of how to do this with like the most recent. It's called Golden Cove is the code name, but it's the Sapphire Rapids model for the processor. And we're just going to boot from our this disk.craf. Craf is just a kind of a simple file system disk format that Symix likes to use, and you can convert a fat file system to it. So what this has on it is a Symix agent, which we just use to download our EFI application to the virtual hard disk. So Symix has this thing called script branches, where you can basically write some code to do something on some condition. So this one basically will run concurrently with the system, and it'll wait 15 seconds. And then very, very technically advanced, it'll input and enter, and then input FS0 to switch to the file system in the UEFI shell. And then it'll run this Symix agent download command, which will download our EFI application that we just compiled. And then finally, it'll run it. So that's what we'll do first. We'll just run it and test it without using the fuzzer. So the you are sharing a window is over top of my stuff. There we go. All right, so now we have this. And then the final thing we need to do is just initialize the project with Symix. So I'll do ISPM, which is the Symix package manager. Create. Create is just shorthand for use all of the packages that you have installed. I only have the x86 open source, like publicly available packages installed here. So this will just install all of them, including the fuzzer package. And because I already put my corpus and EFI application stuff here, we have to ignore existing files. Oops. Sorry, not packages. All right, so you can see that added a bunch of stuff. The only important thing here is the symlinks to the Symix application. So we'll go ahead and run this EFI application. I'm going to run it without GUI because otherwise some windows pop up, which are usually nice if you're running it, but not so great for demos. So system boots up, runs our EFI application, and here's the hex dump of that uninitialized memory. So not super useful to us, but I guess if you want an easy and quick way to simulate running UEFI applications, this is a pretty good way to do it because it's pretty quick to get started. So we'll exit out of this, and then now we'll enable the fuzzing. So it's a pretty simple interface. Basically, all we do is we load the TSFFS module, which we've already installed. And there's instructions for everything here in much greater detail in the repository. If you're actually interested in using this, I would recommend reading those instead of just using this demo. But so the first thing we do is we load the TSFFS module, and then we instantiate it. We create an object. Basically, in the backend, loading the module just creates a class, and then this creates an instance of that class. We'll set our log level to trace just so that we get lots of nice output. And we set it to start and stop on the harnesses that we just compiled into our application. Set a 3-second timeout. If X509 verify cert runs for more than 3 seconds, and this is a virtual time, not a wall clock time. So Symix has its own time because it runs sometimes faster and sometimes slower than the real CPU would run the code. And then we'll add a page fault as an exception, because if we get a page fault during this code, then we're probably doing like a null dereference or something nasty. And by the way, this is the real X509 verify cert, so I don't expect to get any bugs here. This is just for demonstration purposes. All right, so if we run it again, we'll now see that we will run through, and then we'll just keep running in a loop. And off the bat, you can see the test cases changing and we're getting different coverage and all of that stuff. So this is all great, but this is pretty slow. And that's actually just because we're printing. So we'll just do one optimization here. And we'll go up to this and edit our application. And luckily, there's already a pretty standardized way to comment things out for fuzzing. libfuzzer uses this macro, so we use it too. And we'll just if-def out all of our print statements. So that was about half an execution per second, which is not amazing if you're familiar with fuzzing. It's certainly better than 0 executions per second not doing fuzzing, but we can do a lot better than that. I'm just gonna arrow up until I find it. All right, so now if we run, we won't get the nice output, but we will run much faster. And this is closer to the speed you can expect to see if you're actually running this in production. Usually I see about 100 executions per second per core, and you can run as many cores as you have in your system. So it'll scale linearly. Basically, the way it works is the fuzzer uses a corpus directory, and it'll periodically dump its in-memory corpus into that directory and then synchronize from it in case other fuzzers are also dumping executions into that directory.
Yes, unless your CPU starts throttling due to thermal cooling, not sufficient.
Yeah, definitely. So you need good cooling, a pretty strong machine if you want to run this as fast as possible. But it's also really good for just kind of spot checks. If you're working on firmware and excuse me, you're working on firmware, you write a new function that takes some untrusted input, throw a harness on it, run it for a few minutes. If nothing crashes, it's a nice little spot check as you're developing, just because it's so easy to toss the harness in there and run that there's almost no reason not to do it. So that's kind of the primary functionality. That's the fuzzing. You can see we get about 100 executions a second here. there's one more functionality I want to highlight, which is taking advantage of Symmex to reproduce runs. So obviously, we didn't find any crashes here because this is verifying X509 certificates. But if we'd found a crash, we might want to replay it and use Symmex to debug through that crash and see, what's the register state, why are we crashing, what memory are we accessing, etc. So let's just take a look at our corpus. And you can see we've got a bunch of stuff in our corpus. Each entry of the corpus is an input that caused new control flow in the program. So we can already see after just a couple seconds that the fuzzer is making progress. So we can reproduce with one of these inputs by running the repro command. And we'll just pick this one. Whoops, that is my pub key. Not that one. Not my private key, don't worry, anybody. I'm SSH'd into my other computer because Jitsi was having issues on Linux. So if we run repro, we exit because I've done something wrong. All right, let's try it again. I think pasting messed up the buffer. So I guess I don't get perfect demonstration looks, but for the most part, we're good. All right, well, I guess repro mode's not happy today. But in general, usually you can use this and single step through your test case. I think I spelled it wrong actually, but you can single step through your test case, examine all of everything that's going on during execution, and basically just debug why your fuzzer is finding crashes. So, excuse me, I've got a throat tickle, but so basically, there's a few other features that I wanted to talk about. One is basically we have the ability to set various error conditions. So sometimes you want to fuzz for crashes. Sometimes you want to fuzz for, accesses to off-limits memory and so forth. And so we offload this functionality basically just to Symmex, and we say that you can use breakpoints. Excuse me. You can use Symmex breakpoints and set those as fuzzer error conditions. And this allows you to say, you can set a breakpoint on some instruction and say if we execute that instruction, that's an error. You can set a breakpoint on a region of memory and say, okay, if we're fuzzing this SMM handler, like Brian was talking about, and it writes to this region of memory it's not supposed to, that's an error. And you can, of course, use the compiled in assertions to detect errors. So we're hoping in the future this will allow us to support sanitizers with EDK2 and other firmware platforms, either by adding a breakpoint on the ASAN handler or by adding the assertion to the ASAN handler. So that's kind of the next step for us. We're already seeing, teams are starting to use it internally. Some people are messing with it externally, finding some interesting cases. But really, once you add sanitizers to fuzzing, that's how you get, real findings. So that's sort of the next step for us as far as development of this tool. But, so yeah, apologies that I wasn't able to show up the repro functionality, but basically, it sets a bookmark, you reset to the bookmark, you step through the execution. It's reasonably simple stuff. So yeah, that's all I got. So we'll move to questions and discussion.
Rowan,
So-
there's a few questions about like the trade-offs of using VT like for performance, but does that cost you some introspection capabilities?
Yeah, so people who are familiar with CIMIX probably know about VMXMon, which allows us to basically offload most of the execution to the CPU instead of simulating it. And we're working on support for this with the fuzzer, but right now, because we do a trace of the entire execution for coverage, we can't do that offloading.
The heck was that? It's weird.
Yeah. So, Marty, it's your side, or because you're not muted, or this was someone else?
There was a loud bang.
Yeah.
Was it me?
I don't know. Anyway, I guess Rowan, did you answer the question? Like, or you like? Did you finish your answer?
I think so. Yeah.
Okay.
Basically, yeah. In the general case, as far as trade-offs, basically, TSFFS isn't trying to be. It'll never be the fastest fuzzer just because it's running with a simulator instead of even an emulator, much less on bare metal. So our goal is to not be too slow, but our goal is never going to be the fastest fuzzer or anything like that, because it just won't be. If you need 100,000 executions a second, you're just going to have to use KFL or some other hypervisor-based fuzzer.
So if the speed is not the main benefit, what's the main benefit of TSFFS?
Right. So the main benefit is just being able to fuzz stuff that's usually really hard to set up fuzzing for. So like SMM handlers is a good example. Usually those are pretty hard to set up fuzzing for, especially if you need to test an SMM handler that's using a hardware feature. You need to simulate a bunch of it. If you find an issue, you need to figure out if it's an issue with your simulation or an issue with the actual handler. So our goal is really just, if you want to fuzz something, this is kind of the first stepping stone, especially at the UEFI firmware level. Nothing else really has the same amount of like, you can just grab it and go, and just use your existing firmware with a couple lines of code inserted. And you don't even need to insert a couple lines of code. We also have, a closed box functionality where you can just specify region of memory to inject your test case data into. So you don't need to modify your firmware really at all if you don't need to. So basically the main advantage is just usability in general.
So initially you said about the logo fail. Was it found with TSFF?
What was that? Sorry?
Logo fail. Was it found with TSFF?
It wasn't, but I'm working on reproducing, finding it as a fun test case.
Okay. So we have like arms race, like a race of fuzzers to find the vulnerabilities in UEFI.
Yeah, I think it was found by Binarly using some internal fuzzer that they have. So I don't think their fuzzer is open source, but I could be wrong about that.
Yeah. Okay. So you said also OVMF is fuzzed pretty extensively. What areas? Like maybe I have like a kind of two parallel. Like this is like what areas of OVMF were fuzzed and like what you found. And then second thing is you saying it's things are easy to set up for this, but are there any guides for setting up like this fuzzing SMIs, fuzzing of VMF, fuzzing, I don't know what you're fuzzing, your runtime services, or this is more like API exposed in UEFI at UEFI shell level?
Yeah, so when I mentioned OVMF, I was actually mentioning it's been fuzzed pretty extensively with KAFL. So I think there were some findings, but I don't know what there were off the top of my head because I wasn't involved with that effort. But I think some of it is public. If you just look up KFL and OVMF, I think there's some stuff about it. As far as what we have guides for, right now I have guides for fuzzing UEFI applications, kernel and user space on x86 and RISC-V. And I'm working on guides for runtime services and PEI. And basically I'm just going through each level, like each stage of UEFI and making guides for it. So eventually we'll have guides for everything. But
these guides are inside. These guides are inside the TSFF repo.
Yes, yeah. So they're in the docs directory, and then on the right side, there's also a documentation link where it's in site format.
Okay. So other segue. I'm trying. Like, we have like 25 more minutes. I don't want to torture you because I hear you have like this voice. Probably dry air or something. But anyway,
I can just run and grab some water. I'll be fine.
Sure. So the point, but we have next talk at the full hour, yeah. So we have to switch to other topics. But anyway, like you can stay, and maybe later we also will have questions. Like I guess some people will grab some adult beverages, and probably we will sit here for next, I don't know, like 6 hours or 7 hours or something like that. Typically these parties take like 12, 14 hours. But anyway, I want to try to drive discussion into maximizing value and synergy with stuff like Dasharo and open source firmware. So what would be your recommended usage? Like, is it like casual fuzzing or CI/CD like fuzzing, or I don't, what would be kind of maximum value that we can extract from this TSFF stuff?
Yeah, in my opinion, I think there's kind of two use cases that are really good for it. Actually, let me go grab some water real quick, and I'll be back in about 20 seconds.
Sure. Yeah, I guess like I see this link for Intel GitHub. Okay, this is.
Piotr, I just wanted to say that regarding the RE200, I have I've prepared the additional files in order to also screen record, because what I posted in the comments I forgot, that was in my laptop for it, because I can't record, I can't show you live what I'm doing on the same device I'm connected to Dasharo.
Yeah, that's completely fine. Let's get back to that. Like it would be probably in I guess like 1 hour and 20 minutes, something like that. So let's get back to that topic in that time frame. Okay.
I just point that out. I don't have anything else to say until that point. It's fine. Mm-hmm.
Okay, Ron.
Yeah. So the way I see it, there's kind of two use cases that are the best use cases for the fuzzer. So basically, one is you're a firmware developer, you're writing new APIs, you're writing new parts of your firmware, and you want to write small tests for fuzzing small components of firmware, as you go. You write a function that, I'm just going to keep going back to it because it's fresh in my mind. You write a function that parses some image file, write a little fuzzer for it as you're going, run it for a few minutes, kind of to just get, it's free bug finding as far as, you don't have to write as many unit tests up front, and it can help you write unit tests as you go. And then the second use case is CI/CD fuzzing. So Symix is really nice because it can run, like you saw, just in a Docker container. It's not a hypervisor. You don't need to, install a custom kernel or anything. You just kind of install it. Everything runs in user space. It'll simulate your whole stack. So that's actually one of the main things I intend to use it for, is CI/CD fuzzing of things, because you can just add it to your GitHub workflow, have various things fuzz on, pull request or on push, and sort of forget about it. And as we add features to it, obviously it'll become more capable in various areas, as far as like adding sanitizers and things. So it'll continue to improve, but you can already just grab it and use it for CI/CD fuzzing of various firmware components. Yeah, so those are kind of the two.
Yeah, so
primary
I
things.
first use case is not very, I will not say it's very interesting in my opinion, because it's unlikely to write new API when you're using frameworks. You typically don't do that. I guess like UEFI core developers do that, but you don't fuzz core boot with that. You know, you fuzz UEFI stuff. Yeah. Okay. But the second case with CI/CD. So can you tell more about that? Like, do you have any examples of setup or GitHub workflows that do it? Maybe it's like effortless for us right now, or maybe I don't know, like 8 hours of work will enable that kind of additional checks. And we would be very happy to share that during the next Dasharo user group, for example, and vPub. How hard it is and what does it involve?
Yeah, so the hardest part for me is figuring out how to build the target software in CI. There's some examples. I guess probably the best example right now that I have is just the test workflow for the fuzzer itself. Obviously, part of our tests in our GitHub is running the fuzzer on some example projects with UEFI applications and things. So our test workflows that are running, they basically have an iteration limit, and so they run for 100,000 iterations in CI and then stop, just to make sure that the fuzzer is working for all of the things that we expect it to work for. But basically, your setup for fuzzing something in CI would be the same. You just wouldn't be targeting a test. You'd be targeting the real firmware.
So for me, very interesting kind of guide would be CI/CD with TSFF for OVMF build. That would be very interesting. And we already have CI/CD because today we released Dasharo for QEMU Q35 version 0.1. It's essentially OVMF plus some Dasharo stuff, as I said in the roadmap presentation. So adding the TSFF to that, if it would be possible. Also, I wonder what kind of how much credits you eat with this kind of like, would it be possible with GitHub free account, or you need some like also we can delegate that to some workers inside 3MDev lab. Now that's completely fine, but the point is, the biggest problem for me, at least right now, it's not the building of the firmware, is how to add the fuzzing part. Yeah, how to put in the workflow the TSFF.
Right. Yeah. So I guess I think you have a good point as far as that would be. I mean, that would definitely be a good example. And covering the CI/CD and the documentation isn't something I've gone through yet. I've been more focused on just the individual use case, but I can absolutely add the OVMF example.
So I'm just telling that to you. If you want adoption in that ecosystem, that's one of the options that I see, because in first use case I don't see adoption, or if you have other use case, then we can think about. So TSFF can be used from operating system trying to kick the runtime services and do something with runtime services, or this is not the TSFF use case?
No, it should be totally usable for runtime services.
Okay. Do you have like guides or something about that, or this is not yet? Not yet.
Not yet.
Okay.
All of this is definitely on the roadmap, but yeah, lots to do in little time. Classic problem.
So I will tell you like this: like, you have to report roadmaps, and then you have to report that you delayed roadmap, and then you have to regret, and then you will do this. That's lesson that we kind of exercise in the Dasharo community. But from time to time, it is also some magical synergy with some other people. and suddenly there is more people to achieve the same goal, and it's easier to get that. Yeah.
Definitely.
Mm-hmm.
Yeah.
Brian,
So
Brian also gives some ideas. Mm-hmm.
yeah, the regression testing is a really good point, because one of the kind of core ideas of fuzzing is you start with a corpus of inputs. So if you already have fuzz testing in place for a lot of your code, regression testing becomes as simple as just putting the input that caused the bug into your corpus and letting it continue to run. Now, of course, the question becomes, why didn't the fuzzer find it if you're already fuzzing the API? But sometimes these things happen. Like a good example is the big bug in WebP for Chromium a while back. There actually was fuzzing that was fuzzing the area of code that was affected, but the bug was so complicated that it could only really be triggered by manual analysis until you figure out what you have to set 18 numbers to the correct value, and then suddenly a new code path opens up. So once manual analysis finds that, and that's it's unfortunately a downside of fuzzing is that even though it's smart randomness, you're still using randomness. But the upside is you can help the fuzzer a lot by adding new test cases as you do this regression testing. So thanks, Brian. That's a good point. I forgot about that whole side of stuff.
Yeah. So maybe other piece. If what you would expect, like what we would expect from community like open source firmware community, what will be your idea for engaging those people that came to this, like 30 people? Probably some people will watch this on YouTube. We probably don't know how many people really see this discussion, but like what you will expect from those people, and maybe a little bit about the future, like let's say next quarter or two, how you see TSFF evolving, what direction maybe you working, or I guess about the things you can say, not about the things you cannot say.
Yeah, obviously, since I work at Intel, a lot of my focus is internal and helping our teams, adding features to the fuzzer that allow our teams to use it for the things they need it for. But I guess my idea for community engagement is sort of the same, and that, if somebody comes to me like you just did with an idea about improving the documentation to add, here's how you run it in CI, here's how you run it for various components of EDK2. If people come to me with ideas that I think are, applicable and I can justify to add to the tool, we're going to add it, because basically our goal is not just create a fuzzer that's really good at fuzzing one thing at Intel. The goal is, let's make it easy to fuzz firmware, kind of in the general case, and whatever tool people need to get that done is kind of what I want to build. So if one of the things a tool that fuzzes firmware needs to do really well is work really well in CI, or scale across a cluster or whatever it may be, we're just going to add those features and not really think too hard about it. As far as future plans, there's some concrete future plans. Obviously, one is, and kind of the main one, is to get sort of scaled fuzzing of a lot of open source stuff going using the tool. So fuzzing a lot of the EDK2 APIs is kind of the first thing. Getting sanitizers working while fuzzing those APIs is another big thing. And obviously all of that fuzzing would kind of fall under the realm of CI fuzzing as well, for all of those APIs. Improving the documentation is the other really big side of, right now the fuzzer is pretty capable, and there's a lot of use cases that it can handle, but I don't think anybody but me would be able to sit down and set it up for those use cases. So kind of just putting pen to paper and creating examples, creating tutorials, and creating walkthroughs for all the various different, like right now I'm working on, in EDK2 platforms, we have the Symix open board package, which has a bunch of platform initialization, it has runtime drivers, it has everything. So what I'm working through is kind of going through every stage of the UEFI cycle, adding finding a place that seems fun to insert a bug, I'm inserting a bug, and then I'm showing how to harness and fuzz and find that bug at that stage of UEFI, and what you need to change to build it, or what you need to change to harness it, and what the best setup is, optimizing for speed and all of that type of thing at each stage. So documentation is a big one. Obviously, it's also fortunately the slowest part of the process. So yeah, Andrew, good point. But if I find real bugs, those are gonna go in the paper first. So
yes. Do you by any chance know Tamas, who is also a colleague of yours at Intel?
Yep, I'm on Tomas's team, so we work together.
Right. So I do a lot of work with Tamas and his fuzzing projects at the moment. Yes, my impression is that nothing really survives very long against these fuzzers.
Yeah, it really, for the most part, that seems to be what ends up happening. Is once you get a tool that's able to fuzz something that hasn't really, even if it has been fuzzed before, hasn't been adequately fuzzed and had attention paid to it to make good fuzz test cases, not just send an input to the whole app, but harness the parts of it that seem interesting, or various runtime drivers. That, I guess, if we're talking about the UEFI portion, bugs tend to start falling out really fast when you do that. So
a technical equivalent of the legal saying would be bugged until proven otherwise.
yep, definitely. Yeah,
Okay.
that's kind of the main motivation for getting sanitizers going. Is the fuzzer's good, and you can find various classes of bugs with it, but until you get sanitizers, you're kind of leaving a lot on the table as far as memory issues and defects that don't necessarily cause a crash, but are causing vulnerabilities in your application. So
yeah, I guess we slowly should wrap up. But what I want to say is, like, I have to say that I really appreciate that you and Brian joined today vPub. You are very welcome always. If you will plan to update things, want to say something more to community in future vPubs, feel free to ping me, let me know that there is some topic you want to talk about. As I said, your work is very important for improving quality of the open source firmware ecosystem. Of course, also closed ecosystem as a I guess probably my primary goal for you. But on the other side, those things are very important, and I hope, as Brian said in his presentation, I hope we can slowly, as resources allow, move things forward into integrating those great projects both STM, TSFF, of course this CI/CD area, which is interesting, and bring value to people, show value to people that together, collaborating, we can improve security, improve trustworthiness of those systems, and of course improve privacy thanks to that. Hopefully making better solutions that everyone enjoy, and of course that should also contribute to our career. It should contribute to user experience and growth of Dasharo community. Of course, as a side effect, also to growth of other communities, which like Coreboot or EDK2 or TSFF. And of course, I guess STM is I don't know if we can call it community, but it's very niche. But maybe at some point there will be community around STM. So thank you very much for that. And if you will have any talks in future, please let us know. And that's it, I guess.
You bet. Thanks so much for having us. This is a great forum, so I'm really glad that this is my first intro to it. So nice to meet you all.
Yeah. So if you want to hear like even more hardcore stuff, stay longer, because some discussions here are like bizarre sometimes. So we essentially discuss privacy, trustworthiness, open source firmware for every level of the market, every market segment, from microcontrollers to the servers, and sometimes, of course, touching like sensitive topics of philosophy and other aspects of related with trust, related with privacy. But yeah, and there are very interesting people coming here, very interesting people with very interesting threat models. Sometimes real, sometimes imaginary, but yeah, that's why we're doing this ninth time, like it's already ninth vPub, and we probably will do it in future. Yeah, any inputs on how Dasharo would like to fuzz are also welcome. We develop as we develop tools, of course. Yeah, I guess like, yeah, I guess we are kind of at early stage of evolution, way earlier stage of evolution, and we have definitely way less resources to like put a lot of energy into like someone fuzzing. I know that this has value. I understand that, but the point is we have, like, I would say, more serious problems. Like, for example, one serious problem is that we are stuck on some old version of EDK2, and that's something that we have to fix. And that's my main headache. Also, like, for example, we see a lot of problems with UEFI secure boot, and this is something that we would like to improve, and we would like to be state-of-the-art implementation of UEFI secure boot that others can tell, like take a look, like Dasharo guys did that, and because like reference implementation from EDK2 is kind of problematic and is confusing, and then of course everyone repeat the same scheme, and users are even more confused. And so UEFI secure boot is something that we want to improve a lot and bring to end users, not just, we don't want this to be something niche that just some people use. And of course there is strange boot, there's like a lot of other stuff. If we could enable fuzzing like effortless, without much effort, that would be great. Then maybe if we will discover the values, we can extend on that. Yeah, but also we are not in offensive security, so we are not in bug hunting or bug bounty area. So that's yeah.
Yeah, there are more than enough bugs to be had without going looking for more.
Yeah.
How can you enjoy the current bugs without looking for more?
Because the to-do list already has enough interesting ones on them, mainly from other people fuzzing Zen and coming along and with interesting findings.
Yeah. So
as they say, the rabbit hole never ends.
So Andrew, someone's actively fuzzing Zen?
Yes, there is a couple of PhD students in Japan who have actually done a fuzzer for nested virtualization implementations. And they are the proud owner of some CVEs against KVM for it. They have been very good. They've come and reported some bugs against Zen. They have not got any CVEs because it is outside of our security support, but they are coming along. They found 3 interesting bugs, including one that was put in trying to fix an original trench boot bug, which I just messed up completely. The sad thing there was they ended up triggering a code path that it was only supposed to be used for Intel TXT, but no one ever said that, and no one wrote in the manual, don't do this unless you're Intel TXT. So of course some people went and did it with it's the how TXT holds the CPUs in wait for SIPI state, which they do inside VM. So all the VM controls let you go into the wait for SIPI state. And if you're not careful with nested virt, you can do this on a real system and send out the sideband wait for SIPI message or the sideband shutdown message, which of course causes unintended consequences for the rest of the system.
Yeah. So Andrew, thanks for those information about Zen fuzzing and these achievements. Like we have one more segment with Han Etzer about the AMD and his crusade to bring open source firmware to AMD AM4.